Deep in the suffocating heat of Colombia's Cerrejón coal mine, where industrial excavators strip away layers of ancient earth like pages from a geological book, paleontologist Dr. Carlos Jaramillo was examining what appeared to be routine Paleocene fossils when he encountered something that would force science to completely recalculate the upper limits of what vertebrate life could achieve on Earth. Working through sediments that had preserved an entire tropical rainforest from 60 million years ago, his team had been methodically cataloging the compressed remains of leaves, fish, and crocodiles when they uncovered a vertebra so massive it defied immediate classification. The bone was thicker than a human wrist, with proportions that seemed to belong to some nightmare creature from science fiction rather than the fossil record of our planet. At first, the research team did exactly what any reasonable paleontologist would do when confronted with oversized reptilian remains in Paleocene tropical deposits. They assumed they were looking at crocodile bones. Crocodilians had dominated the waterways of post-dinosaur Earth, and the idea of finding large predatory reptiles in ancient swamp deposits was hardly surprising. But something about this vertebra was fundamentally wrong. The proportions didn't match any known crocodile anatomy. The curves were too pronounced, the neural arch too compressed, the overall architecture designed for a completely different type of locomotion. As more bones emerged from the ancient mudstone, dozens of vertebrae, massive ribs, and skull fragments, one terrifying possibility began to crystallize in the minds of the research team. What they were excavating wasn't a crocodile at all. It was a snake. And not just any snake, but a serpent so enormous it challenged every assumption about the biological limits of vertebrate growth and the environmental conditions necessary to support such impossible creatures. At first, scientists dismissed the initial size estimates as calculation errors or misidentified specimens. The idea that a snake could grow to the dimensions suggested by these fossils seemed to violate basic principles of reptilian physiology and ecological energetics. Snakes were supposed to be relatively modest predators, constrained by their ectothermic metabolism and the mechanical limitations of their elongated body plan. But as the excavations continued and more complete skeletal material emerged, the measurements became undeniable. What emerged from the Colombian coal deposits was evidence of Titanoboa cerrejonensis, a serpent that stretched over 42 feet in length, weighed more than 2,500 pounds, and possessed a body diameter thick enough that a grown man could barely wrap his arms around its midsection. To understand why Titanoboa represents such an extreme biological achievement, you have to understand the fundamental constraints that limit snake size in modern environments. Contemporary serpents follow predictable scaling relationships where body length correlates directly with vertebral dimensions, metabolic requirements, and environmental temperature tolerance. These mathematical relationships have been refined through decades of studying thousands of living snake species across every conceivable habitat on Earth. When paleontologists applied these established scaling laws to Titanoboa's vertebrae, the results seemed to defy biological possibility. The largest reliably measured snake in recorded history, a reticulated python from Southeast Asia, reached approximately 28 feet in length and weighed around 550 pounds. Titanoboa exceeded those dimensions by factors that pushed the mathematics of snake biology into entirely uncharted territory. Recent biomechanical modeling has revealed that a snake of Titanoboa's proportions would face physiological challenges that no modern serpent encounters. The cardiovascular system required to pump blood through 42 feet of muscular coils would demand heart dimensions and pumping pressures that exceed those of any known reptile. The neural control systems necessary to coordinate movement across such an extended body would require information processing capabilities that approach the limits of reptilian nervous system architecture. But perhaps most remarkably, the metabolic demands of maintaining such a massive body would require energy acquisition rates that seemed impossible given the hunting strategies employed by modern large constrictors. A 2,500-pound snake would need to consume prey animals weighing hundreds of pounds on a regular basis, requiring hunting success rates and digestion efficiencies that exceed those of any contemporary predator. The mechanical challenges of movement present equally daunting obstacles for an animal of Titanoboa's size. On land, the snake's own weight would create crushing internal pressures that would compress vital organs and restrict blood flow through key anatomical structures. The muscle contractions necessary to lift and manipulate such a massive body would require energy expenditures that could quickly exhaust the animal's metabolic reserves. Yet somehow, for millions of years during the Paleocene epoch, Titanoboa not only survived but thrived as one of the dominant predators in South American ecosystems. The snake's success suggests that the environmental conditions of its era provided solutions to biological challenges that seem insurmountable from our modern perspective. To understand how Titanoboa could exist, you have to reconstruct the extraordinary environmental conditions that characterized Earth during the Paleocene epoch. This was a planet transformed by greenhouse conditions so extreme they created biological possibilities that no longer exist in our current climate system. Global average temperatures exceeded modern levels by 8 to 10 degrees Celsius, creating tropical conditions that extended from the equator nearly to the polar regions. The Colombia of 60 million years ago bore no resemblance to any modern environment. Year-round temperatures averaged above 32 degrees Celsius with minimal seasonal variation, creating a perpetual sauna that never provided relief from the sweltering heat. Humidity levels approached saturation, turning the entire landscape into a steaming greenhouse where evaporation and condensation cycles created constant precipitation and fog. This wasn't simply a warmer version of today's tropical rainforests, it was a fundamentally different type of ecosystem that operated according to biological principles that have no modern analog. The extreme temperatures created metabolic conditions that enabled ectothermic animals to achieve growth rates and body sizes that would be impossible in contemporary environments. For cold-blooded reptiles like Titanoboa, these greenhouse conditions removed the primary constraint that limits snake size in modern ecosystems, temperature-dependent metabolism. Ectothermic animals can only grow and function as efficiently as their environmental temperature allows. In cooler conditions, their metabolic processes slow dramatically, reducing growth rates, digestion efficiency, and overall activity levels. But in the blast furnace environment of the Paleocene, Titanoboa's metabolism could operate at maximum efficiency year-round. The snake never experienced the metabolic slowdowns that constrain modern serpents during cooler periods. Its digestive system could process enormous meals rapidly, its muscle contractions could generate maximum power output consistently, and its growth could continue at optimal rates throughout its extended lifespan. Recent climate modeling studies have revealed that the atmospheric carbon dioxide concentrations during the Paleocene exceeded modern levels by factors of 3 to 4, creating greenhouse effects so intense they eliminated seasonal temperature variation across most of the planet. This created biological conditions that have no contemporary equivalent, environments where the fundamental constraints governing animal physiology operated according to different rules. Titanoboa's hunting strategies reflected adaptations to an aquatic environment that maximized the advantages of enormous size while minimizing the mechanical challenges that would make such dimensions impossible on land. The snake wasn't a terrestrial predator struggling against gravity, it was an aquatic ambush hunter that used water's buoyancy to support its massive frame while exploiting the physics of fluid dynamics to achieve hunting capabilities that would be inconceivable for a land-dwelling animal. The Cerrejón ecosystem preserved in the Colombian coal deposits reveals a landscape dominated by vast river systems, permanent wetlands, and swampy forests where water levels remained high throughout the year. In this aquatic labyrinth, Titanoboa could move with surprising grace, its massive coils supported by water density that eliminated the crushing weight that would make terrestrial locomotion impossible. Underwater, the snake became a biological submarine capable of remaining motionless for extended periods while monitoring its surroundings for potential prey. Its enormous size, which would be a liability on land, became a tremendous advantage in aquatic ambush hunting. Large prey animals approaching water sources would be unaware that what appeared to be a submerged log or root system was actually a predator capable of explosive acceleration. Biomechanical analysis of Titanoboa's vertebral structure reveals adaptations that optimize the snake for rapid underwater strikes rather than sustained terrestrial locomotion. The neural spines and transverse processes show modifications that enhanced lateral muscle attachment points, enabling the powerful side-to-side undulations necessary for aquatic propulsion. These anatomical features suggest that Titanoboa was essentially a giant aquatic constrictor rather than a terrestrial serpent. The constriction capabilities of such a massive snake would have been absolutely devastating. Modern large constrictors can generate pressures sufficient to stop blood circulation in their prey, but Titanoboa's size would have enabled it to apply forces capable of crushing bone and completely collapsing the respiratory systems of even large vertebrates. Prey animals enveloped in Titanoboa's coils would have faced pressures exceeding 400 pounds per square inch, forces sufficient to instantly incapacitate crocodiles, giant turtles, or any other large animal unfortunate enough to encounter this aquatic apex predator. Recent studies of the Cerrejón fossil deposits have revealed that Titanoboa shared its environment with prey species perfectly suited to supporting such a massive predator. Giant turtles with shell diameters exceeding 6 feet provided concentrated sources of protein and calcium. Early crocodilian species, while formidable predators themselves, were still significantly smaller than Titanoboa and would have been vulnerable to ambush attacks in confined waterways. The existence of Titanoboa reveals the operation of ecological principles that no longer function in modern environments, ecosystem dynamics that could support predators of such extraordinary dimensions through prey abundance and resource availability that have no contemporary parallel. The Paleocene tropics operated as biological manufacturing systems capable of producing the enormous quantities of food energy necessary to sustain apex predators weighing over a ton. The extreme greenhouse conditions of Titanoboa's era created plant growth rates that far exceeded anything observed in modern tropical ecosystems. Photosynthesis operated at maximum efficiency year-round, with high atmospheric carbon dioxide concentrations and optimal temperatures combining to drive primary productivity to unprecedented levels. This botanical abundance supported herbivore populations of corresponding magnitude, creating prey communities dense enough to sustain predators of Titanoboa's enormous caloric requirements. But the ecological relationships that supported Titanoboa extended beyond simple predator-prey dynamics to include complex interactions between multiple apex predator species that partitioned resources according to size, habitat preferences, and hunting strategies. The Cerrejón deposits contain evidence of giant crocodiles, massive turtles, and large birds that collectively dominated different aspects of the aquatic ecosystem without direct competition for identical resources. This predator community structure enabled Titanoboa to specialize as the largest aquatic ambush hunter while coexisting with other formidable species that exploited different hunting niches. The snake's enormous size made it uniquely capable of capturing and consuming prey animals that were too large or dangerous for other predators to handle safely, creating an ecological role that has no modern equivalent. Recent isotopic analysis of Titanoboa bone chemistry has revealed dietary patterns consistent with specialization on large-bodied prey species rather than the more generalized feeding strategies employed by most modern large constrictors. The snake appears to have focused its hunting efforts on capturing individual prey animals that could provide massive caloric payloads rather than pursuing smaller, more numerous targets. This feeding strategy makes perfect sense for an animal of Titanoboa's proportions. The metabolic costs of hunting and the mechanical challenges of manipulation would favor prey capture events that maximized energy acquisition while minimizing the frequency of hunting episodes. A single giant turtle or large crocodile could potentially sustain Titanoboa for weeks or months, allowing the snake to remain sedentary while digesting enormous meals. Titanoboa's extinction provides crucial insights into the thermal limits that constrain vertebrate gigantism and the fragile environmental conditions necessary to sustain biological extremes. As global temperatures began declining during the late Paleocene and early Eocene epochs, the snake found itself trapped by the same temperature-dependent physiology that had enabled its extraordinary growth during the preceding greenhouse period. The cooling trend that ultimately eliminated Titanoboa wasn't dramatic by geological standards. Global average temperatures decreased by only 3 to 4 degrees Celsius over several million years. But for an ectothermic giant dependent on extreme heat to maintain optimal metabolic function, this relatively modest climate change created cascading physiological challenges that proved insurmountable. As temperatures declined, Titanoboa's metabolic rate decreased proportionally, reducing the efficiency of digestion, muscle contraction, and growth processes that were essential for maintaining its enormous body. The snake's massive size, which had been an advantage during the greenhouse conditions of its heyday, became a liability as cooler temperatures made it increasingly difficult to acquire and process sufficient food energy to sustain such an enormous frame. Recent climate modeling studies have revealed that Titanoboa likely faced a thermal threshold below which its physiology simply couldn't function effectively. Modern large constrictors require environmental temperatures above 25 degrees Celsius to maintain optimal metabolic function, and an animal of Titanoboa's proportions would have needed even higher temperatures to overcome the scaling challenges associated with its massive size. The ecological systems that supported Titanoboa also collapsed as global cooling progressed. Plant productivity declined with falling carbon dioxide concentrations and reduced temperatures, diminishing the primary productivity that had sustained the abundant prey populations necessary to feed giant predators. The dense, year-round tropical forests that had characterized Titanoboa's habitat gave way to more seasonal environments where lower temperatures and periodic drought stress reduced ecosystem carrying capacity. But Titanoboa's extinction wasn't simply a matter of individual physiological failure, it reflected the breakdown of entire ecological networks that had been finely tuned to greenhouse conditions. As the dominant herbivores that had served as Titanoboa's prey began declining due to habitat changes and cooling temperatures, the snake found itself at the top of a collapsing food web with diminishing resources and increasing energetic stress. The discovery of Titanoboa forces us to confront the profound influence that global temperature regimes have on the fundamental limits of animal size and the types of biological communities that can exist under different climatic conditions. This snake represents evidence of biological possibilities that emerge only under environmental extremes, revealing that life's potential extends far beyond what we observe in contemporary ecosystems. Titanoboa existed because the Paleocene Earth created thermal conditions that pushed ectothermic physiology to its absolute limits, enabling metabolic performance and growth rates that have no modern parallel. The snake's enormous size wasn't an anomaly or evolutionary accident, it was a direct consequence of environmental conditions that removed the primary constraints governing reptilian biology and allowed natural selection to explore size ranges that are impossible in our current climate. Understanding Titanoboa provides crucial insights into how future climate change might affect animal communities and ecosystem dynamics. As global temperatures rise due to anthropogenic greenhouse gas emissions, we may begin to see biological responses that echo the conditions that produced giants like Titanoboa during the Paleocene. Ectothermic animals in warming environments are already showing increased growth rates, expanded body sizes, and enhanced metabolic performance that reflect the same thermal relationships that enabled Titanoboa's existence. But Titanoboa also serves as a warning about the fragility of biological extremes and the rapid ecosystem changes that can result from relatively modest climate shifts. The snake's extinction demonstrates that even perfectly adapted organisms can be eliminated by environmental changes that fall within the range of natural climate variability, highlighting the vulnerability of specialized species to shifting thermal regimes. Recent paleoclimatic research has revealed that the greenhouse conditions of the Paleocene were not unique in Earth's history but represent one example of recurring thermal maxima that have periodically created opportunities for biological gigantism throughout geological time. These thermal spikes, driven by volcanic activity, asteroid impacts, and other geological processes, have repeatedly reset the parameters governing animal size and ecosystem structure. Titanoboa represents a snapshot of life's potential under thermal conditions that exceeded anything in human experience, offering a glimpse of biological possibilities that emerge when environmental constraints are pushed to their limits. The snake's existence proves that life can achieve dimensions and capabilities that seem impossible from our contemporary perspective, but only under environmental conditions that are themselves extreme and temporary. In the end, Titanoboa stands as testament to evolution's capacity for achieving the impossible when conditions align perfectly, and to the fragile balance of environmental factors that constrain and enable life's most extraordinary expressions. This giant serpent existed for millions of years not despite its impossible proportions, but because the Earth itself had become impossible, a greenhouse world so extreme it could support biological giants that challenge our understanding of what life can achieve when physics, chemistry, and evolution conspire to push the boundaries of possibility to their absolute limits.